Hey guys, sorry that I couldn't be with you today, but I know that you're going to be in great hands. So I wanted to take you through your lab and also do a quick review of what you should have picked up when you came into the classroom and the last concept that we talked about on Friday, which was molarity. So when you came into the classroom today, there was the quick review worksheet, that thing. There are 6 pages of the quick review. The quick review focuses on semester 1 topics. So you won't see a lot of our our term 2 topics on it because those should be relatively fresh in your memory. Remember, the quick review is not a complete review of everything you should do for the final that you're taking on December 21st. It's just a jumping off point. So start here. If you don't know what you're looking empirical formula, go in your textbook. Go to the index, look up empirical formula. Find where it was in your textbook. Find out what chapter it was in. And then go do an example problem from the book. Go to your unit packet that talked about empirical formula. Look at your problems and then work your way through. If you do one a week, you're going to be pretty close to being done beforehand. If you do 2 a week, you're going to be done early. So I'm glad that you picked that up when you came in, and the answers are in Schoology. There's just one little catch. You have to put your answers into the quiz first. Then it'll let you look at the answer key. I'm not grading it off of accuracy. I am grading it off of completion. So, quick reviews. Reminder again, your final is December 21st, the last day of school. All right. On Friday, right before you guys left, we talked about 2 ways to describe solutions. We said we can describe solutions using mass percent. That mass percent is the percent of the mass in the solution. This is used when I'm concerned about temperature changes in my equation or temperature changes in my system. I can use percent mass because mass is constant. It does not change on temperature. And the other way that we can describe concentration of solutions is using molarity. And molarity is a derived unit. Molarity is moles solute divided by volume of the solution. And the units on molarity are moles per liter. But we usually label systems just using the capital M, molarity. So if I see capital M, I understand that I'm describing moles of solute in volume of solution measured in liters. Before you left class, I gave you your homework. Your homework was to do the molarity problems in your packet. So do me a favor, grab out your Unit 11 packet. Let's just work through one problem from your packet. The answer key is on Schoology, so please check your work against my work. Let's flip. And let's look at an example problem here quick. So I asked you to compute the molarity or describe the preparation of the following solutions. Let's do number 4. Number 4, what mass of cadmium chloride will be dissolved in 250 cubic centimeters of a 1.50 molar solution? So the first thing I do is I identify what I'm given. They're asking for what mass. They've told me the volume, and they have told me the concentration of the solution. Let me zoom in a little bit here. So my first step is to create a variable list. Molarity equals, moles equals, volume equals. Molarity, they told me the molarity, 1.50 molar. Moles, they asked me the mass. Mass and moles are related, so this is what I'm looking for in grams. And the volume was given to me 250 cubic centimeters. 250 cubic centimeters. But I know molarity is moles per liter, so I need to do a little train track conversion here. 1 liter is 1,000 cubic centimeters. So my centimeters cubed cancels, and this is 0.250 liters. I have molarity, that's the accepted label. I have liters, that is the accepted label. I'm solving for moles so that I can convert to grams. I write my equation in variable form. Molarity is moles divided by volume. I solve my equation for my unknown. I am searching in this case for moles, so I multiply by volume. So I get moles equals volume times molarity. Volume is 0.250 liters. Molarity is 1.50 molar, which gives me, grab my calculator here, grab your calculator too, writing along with me, 0.250 times 1.50, 3 sig figs, 3 sig figs, 3 sig figs, I get 0.375 moles. And I check, what did they want? They wanted amount, but they wanted in mass, not moles, so I have to do one more step. So I take my mole value, 0.375 moles, and I do a train track, 1 mole, and I'm going to convert it into mass of cadmium chloride. So I go to my periodic table, I find cadmium, here's cadmium, 11240, I find chlorine, here's chlorine, 35.45, I have 2 of them, 35.45 times 2, 2 chlorines plus 1 cadmium, 11240, add them up, and my molar mass of cadmium 2 chloride is 183.3. 183.3 grams. Mole label cancels because they are diagonal to each other, and I multiply. 0.375 times 183.3. Show you the math. 0.375 times 183.3, and this is my math value. So 3 sig figs, 3 sig figs. Let's just make life easy. Let's pretend there's a decimal point there. 3 sig figs. 3 sig figs. Let's round to 3 significant figures. 68.7. Keep the 6, keep the 8, keep the 7. The 3 falls off. The answer is 68.7 label grams of cadmium chloride. Boom. So your homework. This was your homework from Friday. Homework from Friday, November 30th. Please make sure that you finish this worksheet if you haven't already. You can check your answers against the answer key in Schoology. All right, so let's talk about today. You can put your packet away for a moment, and let's talk about today's lab. So on your way in, you received your lab protocol, and today we're going to practice working with the molarity equation. So bring this out. I have my highlighter, I have a pencil, and let's pre-lab this. So it is lab partner. Write down your lab partner's name. I'm working by myself. It's Monday, December 3rd. The purpose is to calculate the amount of solute in a 10 milliliter sample of a 4.80 molar sodium chloride solution. So my solute is sodium chloride. I'll be working with 10 milliliters, and I'm going to take this 4.80 molar sodium chloride solution. 4.80 molar sodium chloride solution. It is in the fume hood. There are 3 bottles. So you are going to take your stuff to the fume hood when you're getting it, leave them in the fume hood, come back to your lab station. So the focus of our lab today is to apply the concept of molarity and use this mathematical relationship to quantitatively use lab technique to evaporate the solvent from the solution and to communicate the quality of our lab technique by calculating our percent error. So first, let's write down our equations that we're using today. Our molarity equation. Molarity equals moles of solute divided by volume of the total solution. This will be in moles. Volume will be in liters. And when we are all done, we are going to calculate our percent error. And our percent error equation percent error equals the absolute value of experimental minus accepted divided by accepted times 100. That will give us our percent error. And we are not as much worried about what your percent error is, but interpreting what it means. Like, what did you do in lab? How is what you did in lab being communicated in your percent error? So, before you begin, calculate the theoretical amount of solute that would be in a 10 milliliter sample of a 4.8 molar sodium chloride solution. Show your work in the space provided in the data calculation section. So, where is that at? Data calculations. Here. Calculate the theoretical mass of salt in a 10 molar 4.8 or 10 milliliters of a 4.8 molar sodium chloride solution. Show your work. All right, you have 10 milliliters. You have a 4.8 molar solution. I want to see molarity equals, moles equals, volume equals, and then ultimately I want the mass of the salt. This is your theoretical mass. This is what you will use in your percent error calculation. Percent error equals experimental. This is what you get from lab today when you evaporate. Minus accepted. That's this number up here. Divided by the accepted. Still this number. Times 100. I want to see the equation. I want to see your work here when you calculate your percent error. So in order to do any of our calculations today, we need to know theoretically how much salt is in 10 milliliters of a 4.80 molar solution. Okay, so step one, before you begin, calculate the theoretical amount of solute in the 10 milliliter sample of a 4.80 molar sodium chloride solution. Show your work in the data. Then, collect and wash all glassware needed. So let's figure out what we're going to need in lab today. We're evaporating a solution. So in lab, we will need an evaporating dish. Evaporating dish. Always check your evaporating dish for any hairline fractures that could exist in the porcelain. So I don't see any. We're good to go. I have an evaporating dish. When I evaporate my sodium chloride solution, once it starts to get dry, that salt is going to want to pop. I want to prevent any loss, so I will want a watch glass. So note the watch glass goes on so that the concave part goes into the evaporating dish. So glassware, evaporating dish, and watch glass. Also, I will want a 10 milliliter graduated cylinder. So make sure you're grabbing a 10 milliliter graduated cylinder and not a 50. So collect and wash all glassware needed. Then measure out 10.0 milliliters of the 4.80 molar solution. So what I want you to do, because it's going to be extremely hard, I'm going to flip my camera up here. I'm going to flip you around. Okay. What I want you to do when you're, hi, really close. Okay, so you have your solution, and if you attempt to actually measure exactly 10 milliliters into here, you're going to take forever over at the fume hood. So you're going to take your solution, and you're going to get as close to 10, okay, well, such is life. Get as close to 10 as you can, but it's okay to go over. It's not okay to go under, but it is okay to go over. Then get a pipette from the back cabinet. Go to your lab station. Put your glassware onto the counter. Onto the counter. And what you're going to do, squeeze the pipette bulb. Squeeze the bulb. Place it into the graduated cylinder and remove liquid until you get to 10. Ta-da! Put the salt water excess into the sink. Not a big deal. And now I have exactly 10 milliliters, 10.0 milliliters of my sodium chloride solution. And everyone isn't waiting for 5 years for me to be the perfectionist that I am and get exactly 10 from the fume hood. So I have my 10 milliliters of sodium chloride solution. I have washed I've washed and dried my evaporating dish, my watch glass. So it says next to mass. So let's go back to our lab protocol. Flip. Collect and wash, measure 10 milliliters. This is in the fume hood. And then remove excess with a pipette. Okay. Mask the clean, dry evaporating dish and watch glass. There are electronic balances at your lab station. So mask those, record the values in the data table. Right? Record the values in the data table. Evaporating dish and watch glass. It's going to go right here. And we're masking those in grams. Transfer your 10 milliliter solution into your evaporating dish. Cover the evaporating dish with a watch glass. And then using a Bunsen burner and ring stand, evaporate the solvent from the solution until the sodium chloride sample is completely dry. So let's check out your setup. I'm sorry guys, I'm like flipping back and forth constantly here. All right, I have my ring stand. I have my Bunsen burner. The most important part of your ring stand is about stability. So if your ring stand and Bunsen burner system are stable with your Bunsen burner on here and it's aligned, then rock on. Mine wasn't. So I set it so that, there, let's see if we can get this to focus. Okay. I set it so that it is set to the side. So it's offset. 4-finger height is the ideal height between these two. Grab matches or lighters from the back counter. And then I place my evaporating dish on. I transfer my solution into my evaporating dish. I cover with my watch glass. I light. I place it underneath. And whenever I start heating, I always toast. Toast, toast, toast. Gently, gently heating. And then I'm going to heat strongly. I'm going to watch it. Pay attention so that the mouth of your evaporating dish is not pointing at you, it's not pointing at a table partner. Make sure that it's pointing side to side so that it doesn't have any steam coming out that could possibly hurt you. So we're heating, we're boiling, it's going to start bubbling, it's going to start popping, and I don't want any of that salt to be lost. This is a controlled evaporation, so don't hesitate to take your Bunsen burner, move it, pull the heat slightly away. This isn't a race. This is about being as accurate as we can be. So once we have evaporated all of the salt water out of the salt solution and it's completely dry, so that means there's no water on the bottom of my evaporating dish, there's no steam still coming out, I want to remove the evaporating dish from the Bunsen burner. So I have my crucible tongs. I'm going to pick it up. I'm going to remember hot things look like cold things. Gently place it onto my ring stand so that it cools. I'm going to keep this system together. I'm not going to remove the evaporating dish because there's going to most likely be salt stuck to the bottom of it. So I'm going to cool it on the metal base. I'm going to put my hand above it, feel for the heat radiating off of it. When no more heat radiates off of it, then it's safe to transfer to my balance and mass it. After I have masked it, I'm going to record that mass in my data table. It says heating round 1. Boom, right there. Heating round 1. Record the mass of my system. Right? Then I'm going to put it back onto my Bunsen burner and I'm going to do this round 2 style. So I'm going to pick it up gently. If it's cool to the touch and you can move it with your hands, it's fine. I'm going to transfer my evaporating dish back onto my Bunsen burner, relight my flame, and I'm going to heat strongly for 3 minutes. Heat strongly for 3 minutes. It says reheat dish sample watch glass over strong heat for 3 to 5 minutes. So at least 3 minutes. Cool the evaporating dish with my sample and my watch glass. So cooling. We are masters of transferring here. Notice I put my support hand underneath the joints so that it helps me move things safely. So cool it a second time, and then after it's cool, check for heat, Once it's cool, I'm going to transfer it over to my electronic balance. I'm going to mass it on my electronic balance. I'm going to make my calculations. I'm going to show how fantastic my lab skills are. I'm going to calculate my percent error. Show your work. There are 2 problems. Yay, 2 problems. Do them. Hand it into the basket when you are done. When you are done, your homework is in your packet. Concentration problem review. Monday, 12/3. There's your homework. All right, guys. You're fantastic. Hot things look like cold things. It's salt water. It won't hurt you, but the Bunsen burners can burn you, so pay attention. No hot things on the lab, on the electronic balances. Leave lab better than you found it. All equipment should be returned. If the ring sensors are hot, they can stay. Everything else needs to be returned. If we glance at your worksheet here for just half a second. I know, I've been talking a long time. You're ready to get going. Let me see why this doesn't look. There we go. On the back, you will note there is a conclusion statement. This was our purpose today, to calculate the amount of solute using molarity in lab. I want 3 to 5 sentences. I know, not very much space. But give me 3 to 5 sentences about what you did, how you did it, what you found, what your percent error was, and what happened in lab. So just have that conversation with me, please. 3 to 5 sentences about what you did in lab, and then these are 2 practice problems. Complete those. Okay. You guys are rock stars. Thank you for your good work in lab today. I will look forward to seeing you when I get back to school, and have a great time in lab.